Swayam Prabha. Digital India. Educated India.
I welcome you once again to this class of flow through porous media. We are discussing about this mass continuity. We were talking about the mass continuity in Cartesian and cylindrical coordinates, and we are working with the pressure equations and also the velocities. And in particular, in the last lecture, we are talking about the stream functions and potential functions, and we combine them in terms of complex potential Fz. And we said that in fact we set up a few elemental flows of source, sink, vortex, then we have unidirectional flow. So there are more number of elemental flows. This is not the complete list. You can have a flow like flow of a doublet, flow of other elemental flows are possible, but essentially what I am trying to convey here is how to play with these elemental flows to simulate a complex situation. Okay. So, simulate a situation where you have a well which is continuously injecting water, you have another well which is continuously producing, you have some other type of elemental flows imposed in the porous medium, and then the resultant of all these means if we superpose all these elemental flows, sum them up, and then the summed up Fz, and if we express that summed up Fz as phi plus I psi, and then looking at this psi, looking at this phi, or take that summed up Fz and take the derivative of it, df dz is Wz, and Wz is u minus iv. So, what is u, what is v? So, we can get a fair bit of idea without scratching our head. We just simply taking the elemental flows and summing them up. Okay. So we will continue this exercise. Now we start gradually into superposing different elemental flows. So, let us see what we have now here. Here we are talking about, now we had talked about Fz for source or sink. We said Fz was C ln z. So, Fz was C ln z. So, that is the expression for Fz, and we broke it up. You remember Fz as in the last lecture what we did is we wrote C of ln, and z we have written it as x plus iy, and x is written as r cos theta, and y was written as r sin theta. Then r cos theta plus, so r we have taken out, we have taken r common. So, then it was ln of r cos theta plus I sin theta, and cos theta plus I sin theta we had written it as e to the power I theta. So, this became C ln r e to the power I theta. So, this we had written it as C of ln r plus C of ln e to the power I theta. So, this becomes equal to C ln r plus C I theta. So, then we said that this is the real component C ln r, this is this C theta, not C I theta, C theta, leave out the I. So, this should be plus I C theta. So, C theta would be the imaginary component. So, this is, if we write this as phi plus I psi, then this becomes psi and this becomes phi, the potential function, and we had worked with these phi and psi. Now, if we try to find out what are the velocities in this case, so how will we find out the velocity? Now, the source and sink is particularly important for us, because if we are working with cylindrical coordinate, for example, we are looking at a well. So, for us to define this well, this type of this source and sink type flow is very important. So, now if we take a derivative of this, that is W z is equal to df dz. Basically, we said that W z is equal to df dz, and when we take a derivative of a complex number, it should be u minus I v. This we have seen in the previous lecture. And since this is C ln z, so when we take the derivative of C ln z, this becomes C by z, because the derivative of ln z is 1 by z. So, essentially this W z leads to an expression u minus I v is equal to C by z. That is on one hand df dz is C by z when you take a derivative of this. On the other hand, df dz we have seen in the earlier lecture, df dz is u minus I v. Further, we have studied these in one of the lectures earlier. U can be written as u r cos theta minus u theta sin theta. You may recall that I have these x and y, and at a particular location I have, in the x direction I have u, and y direction I have v. And on the other hand, I have, if we want to work with r theta system, so this is the r and this angle is theta. So, we have this as u r and this as u theta, and then we said that u is basically this is theta. So, component of this u r, so this is u is equal to u r cos theta, and this side you have u theta, this angle is theta. So, this angle is 90 degree minus theta. So, you have this here as minus, because this component of u theta would be there in the negative x direction. So, that is why I have a minus sign here, u theta cos of 90 degree minus theta. So, that is what we see here as u is equal to u r cos theta minus u theta sin theta, and similarly you can see v as u r sin theta this time, because this angle is 90 degree minus theta. So, this is u r cos of 90 degree minus theta, that component, and u theta will have a direct component of cos theta, because this angle is theta. So, this is the v. So, this is the relation last time we had for u and v. This is in fact a sort of vector identity. I mean, whether what type of elemental flow we consider, it does not matter. It will always be u is equal to u r cos theta minus u theta sin theta, and v is equal to u r sin theta plus u theta cos theta. So, in this case, if we try to write what is u minus I v using this expression of this, so instead of u we are writing u r cos theta minus u theta sin theta. So, u is written as u r cos theta minus u theta sin theta. This is what is going in here, and this v is u minus I v. So, this is the v. So, this v is going here, u r sin theta plus u theta cos theta. So, once you have this expression in place, then you can take u r common. So, you have taken u r, we have taken u r common. So, this is one u r cos theta is there and minus I u r sin theta is there. So, take u r common. So, it becomes cos theta minus I sin theta and minus I u theta. So, now we are looking at clubbing this u theta cos theta and u theta sin theta. Mind it, u theta cos theta is a I term. So, I u theta cos theta and minus I square is minus 1. So, that is why you have I square, this is minus plus and then I square again minus. So, finally, it is a minus u theta sin theta. So, if you break it up, this is the expression which you end up with, u r cos theta minus u r into cos theta minus I sin theta minus I u theta cos theta minus I sin theta. So, now you can take this cos theta minus I sin theta common. So, what we are doing here is you are taking cos theta minus I sin theta common, and you are cos theta minus I sin theta common, and then you are getting into u r minus I u theta. If you take this cos theta minus I sin theta and this cos theta minus I sin theta, this if you take common, you are left with u r minus I u theta. And then this cos theta minus I sin theta, we have already seen that this can be written as e to the power minus I theta by Euler's theorem. So, that is why you have written e to the power minus I theta multiplied by u r minus I u theta. So, this is exactly what is going in there. So, u r minus I u theta into e to the power minus I theta. So, in this case you have u r minus I theta into u r minus I theta. On the other hand, u minus I v is c by z. So, this is coming in here, u minus I v, this is coming in here as c by z. So, u minus I v is c by z, whereas u minus I v is this quantity already you have found out. So, now c by z, you can write this z again, you break this z into x plus I y, and this x plus I y you can write once again as r cos theta plus I r sin theta, and then again you can write this as r of r into cos theta plus I sin theta. Then again you can write this cos theta plus I sin theta as e to the power I theta. This is equal to r e to the power I theta using Euler's theorem. So, you can write c by z instead of that c divided by r e to the power I theta, because z is r e to the power I theta. So, c by r e to the power I theta, or in other words e to the power I theta can go to the numerator section. So, it would be c by r into e to the power minus I theta, c by r into e to the power minus I theta. So, then you have if you look at this, so essentially what do we get here? If we clear this entire thing up, you are getting here on one hand u minus I v is equal to u r minus I u theta into e to the power minus I theta. On the other hand, you are getting, so this you are getting from here. On the other hand, you are getting u minus I v here as equal to c by r e to the power minus I theta. So, then if these are to be equated, then this e to the power minus I theta, this e to the power minus I theta and this e to the power minus I theta, they cancel out if we are equating these two. So, you are getting here you are getting u r minus I u theta into e to the power minus I theta, that is equal to c by r e to the power minus I theta. So, you are cancelling e to the power minus I theta and e to the power minus I theta. So, what are you ending up with? C is a real constant. So, c by r is a real term, and on the other hand left hand side you have u r minus I u theta. So, if we match real with real and imaginary with imaginary, there is no imaginary part on the right hand side. So, you will end up with u r, the real part on the left hand side has to be equal to the real part on the left hand side. That means, u r is equal to c by r, that is there, and u theta, which is the imaginary part on the left hand side, there is no imaginary part on the right hand side. So, nothing to match. So, u theta is equal to 0. So, what you have here is u r is basically c by r and u theta is equal to 0. What is u r? U r is the velocity in r direction, and that velocity is, now we are saying it is c by r, and u theta, which is the velocity in theta direction. In fact, that is what our original understanding was, isn't it? Our original understanding was that for a source or sink, we have only radial flow. If it is source, it is going out, and if it is sink, they are all coming in. The direction of the arrow changes. So, in this case, we are saying that if this is a streamline, perpendicular to the streamline, there cannot be any flow. Perpendicular to streamline, only thing that can happen is the potential line, which is the circle here in this case. So, naturally u theta is, so we have this as u r, this is our u r, the velocity in radial direction, and velocity in theta direction, which is u theta. U theta is 0 because there is no velocity perpendicular to the r, because it is a truly a radial system. It is a true source and sink in this cylindrical system. So, we are noting here is that u r existing, u r is existing there, and u theta is 0. U theta cannot exist. Perpendicular to streamline, there cannot be any flow. Further, we note here, you remember last time we said in the previous lecture, we said that u r is, if C is positive, it is a source. Now, we can see if C is positive, then u r is then positive, whereas when C is negative, u r is negative. U r is negative means flow would be inward, not radially outward, flow would be moving inward. So, that is the case when C is negative. This is in fact making perfect sense, because you remember u was, when we were trying to solve this pressure, this Laplace equation for pressure in cylindrical system and only working with r, ignoring theta and z, we said that V r is proportional to 1 by r, right. V r was proportional to 1 by r, mod of V r, that has to be proportional to 1 by r. So, that is exactly what we are heading to, though we do not understand fully what is this C, that we do not have full understanding yet. But this much we understand that V r would be u r equal to C by r is consistent with our earlier understanding that V r is proportional to 1 by r, which we have already established in earlier lectures. So, how to arrive at a more meaningful C? I mean, what is this C? C is some constant we just put in there, but what is this C? So, what we do here is we try to see the meaning of C. In this case, what is the volume flow per unit depth? If we look at per unit depth, we do not need to consider per unit depth as such, but let us see what was this. Let us say I am talking about a cylindrical, let us say I am looking at a cylindrical area with radius, let us say r. Okay. So, let us say I have this height as h. Okay. So, we had discussed this earlier, that this is, here we are talking about a slice. Here we are talking about a slice, that slice has a height h, and all these V r that are coming out through these. See, we are looking at, let us say this is the source, and we are looking at this source has, let us say this is the V r. Okay. This V r is operational, let us say this makes an angle theta. So, V r is operational over this arc length VR d theta. This is the area over which this VR is operational. Okay. So, what we are essentially saying is that this is the VR, this angle is d theta, and VR d theta is the length of this arc, and if you multiply this by the height, so VR, this is the area we are talking about. This area is VR d theta into H, and over, sorry, this area is, I'm extremely sorry, this is VR. So, this arc length is r d theta. This distance is r, this angle is d theta, this is theta, and this is theta plus d theta. So, difference is d theta. So, length of this arc is r d theta. So, r d theta, so r d theta is the length of this arc multiplied by h. So, this gives you the area over which this VR is operational. This is the area over which this VR is acting. So, the amount of flow that is taking place is VR is the velocity in meter per second, then r d theta into h, this gives you the area in meter square. So, meter per second into meter square, this gives you meter cube per second. Okay. So, then you have one has to, but this is for the entire 360 degree one has to do this, then only you can get the total flow. So, that is why you do this integration from 0 to 2 pi. So, that is exactly what they have done here, volume flow per unit depth, and here the integration is from 0 to 2 pi, that is fine. VR they are writing it as UR. I mean, in fact, my earlier terminology was UR and U theta when we started working with this complex potential. So, I think I should be writing it as UR, not VR. So, UR into r d theta into H. Now, since we are talking about per unit depth, so H is equal to 1 in this case. So, that is why this H is not featuring here. So, now if you do this integration here, UR is equal to what? UR is equal to, we had written it as C by R. UR is C by R. That is what we found just in the previous slide, right? Previous slide we found that UR is equal to C by R and U theta is equal to 0. So, that is what our observation was in the previous slide. So, C by R into r d theta, this r will cancel out with this r. So, you are left with C d theta, and d theta, when you do the integration from 0 to 2 pi, you will get, the integration gives you 2 pi. So, this integration gives you 2 pi c. So, volume flow per unit depth is 2 pi c. So, this now gives me a meaning of what is c, because now instead of writing it as C ln z, you can see now we are writing it as f z is equal to minus of q divided by 2 pi ln z. Why? Because volume flow per unit depth which is equal to 2 pi c. So, c is equal to volume flow per unit depth divided by 2 pi, right. So, now we can since the q, there is a sign issue, because if you are producing the well, VR becomes negative. So, VR and q they have the opposite sign. So, one has to keep this in mind. If the q and the VR they are maintained as the same sign, then it will, see, it is basically volume flow per unit depth. This is C is equal to volume flow per unit depth divided by 2 pi. So, that is the definition of C. So, that is what we have done. So, this is basically volume produced per unit depth. So, this is how one can write the complex potential in case of a source with in case of a source in case of the elemental flow for a source. So, q by or volume produced per unit depth divided by 2 pi ln z. When the source is located at position z is equal to z0. See, all this analysis that we have done so far, the source is located at origin, right. Here also the source is located at the origin. So, we have done from the origin, everything is happening. So, now if the source is not located at origin, rather source is located at some other position. This is very important, because if you are working with 3 sources and 2 sinks distributed in the porous medium, and you are trying to find out what is the resultant streamlines. So, in that case, if you pick up one as the one source as the origin, the other sources have to be then deviated from the origin. So, one has to have a general equation for it, and that general equation is ln of z minus z0. I am not fully happy with this, calling this a Q, because last time the Q was flow rate, not flow rate per unit depth. So, we can instead of minus Q, we can still maintain this. Let us say volume flow rate, we have to give some other name to it. Maybe we can give this name as small q, that would be better. So, instead of capital Q, we write this as small q, and then instead of capital Q, we write this as small q, and then we equate this, that q is equal to minus of capital Q divided by H. So, that is because then that would be probably consistent with what capital Q we have defined in previous lectures. Basically, it is the volume flow per unit depth, and if VR is radially outward and it is positive, then the small q is positive, but then if we are looking at the production from the well, which is the reverse of this, then q has to be capital Q has to be negative. So, that has to be accounted. So, anyway, this is these are just the choice. I mean, when you solve problems, you have to put this put these numbers. Best thing, my sincere suggestion here is work with the units, because we are talking about some case volumetric flow, some case volume flow per unit depth. Actually, they have gotten into volume flow per unit depth, because you can see this is directly linked to the stream function, right. So, that is, so in one case we are talking about volume flow per unit depth, in another case we are talking about volume flow rate, another case we are talking about superficial velocity, which is volumetric flux. So, best thing is whenever you work with these, put the units. If you put the units, then you can see the units cancelling out, and you can, moment you see the left hand side is matching with the right hand side, you understand that you are at the right place. So, that is very important for this type of analysis. Anyway, we will definitely if you solve problems in these areas, these concepts will be all clear. This is all I have for this particular module of the lecture. I will continue further. Probably my next attempt would be to superpose a source and a uniform flow. So, if we have a source and uniform flow clubbed together, how this type of flow play out? What would be the resultant streamlines? So, gradually, so source we have already understood by I mean, we made good enough of an understanding with the source. We already understand uniform flow, let us say uz, if we are talking about only the flow in x direction. So, now if we superpose the two, then what would be the resultant streamlines? What would be the resultant velocity profiles in Cartesian system or cylindrical system? So, these are some of the things that I will get into in the next lecture. So, this is all I have as far as today's lecture is concerned. Thank you very much.